How in the world do you get the phenomenal problem-solving power of a quantum computer without the giant, incredibly fragile, and absurdly cold freezers they need to operate? When it comes to humanity's hardest problems, we've been stuck between a rock and a hard place. On one hand, you've got these cryogenic quantum systems. They can do amazing things, but you have to cool them to temperatures colder than deep space. On the other hand, you've got our trusty classical supercomputers. They work just fine at room temperature, but they often get completely bogged down on these complex problems, and they use an absolutely enormous amount of energy. So, what kind of hard problems are we actually talking about? Well, these are the big ones, the kinds of challenges that could help us discover new medicines, invent revolutionary new materials, or optimize global supply chains. I think the best way to picture this is with an analogy. This whole class of problems is called combinatorial optimization, and it's a lot like being dropped into a colossal mountain range, completely blanketed in thick fog, and your one job is to find the absolute lowest point, the deepest valley, in the entire range. So, how does a classical computer try to solve this? It basically just starts walking downhill from wherever it lands. It finds a valley and says, okay, I'm at the bottom, this must be it. It gets trapped in what we call a local minimum, totally blind to the fact that a much, much deeper valley, the real answer, might be just over the next ridge. But a quantum computer has a superpower. It's called quantum tunneling. It doesn't have to waste time climbing all those mountains. It can just, poof, pass straight through them. This allows it to explore the entire landscape almost all at once to find the true global minimum. This is their killer advantage, but it only works inside those crazy cold freezers. But what if there was another way? A third option.